in the 5G, so what do we have? We have communication at two different bands of frequencies, two slightly different. Earlier in the 4 till 4G, all are in the microwave range. There was no talking about of the millimeter wave. Now in 5G, what we have? So we have microwave as well as millimeter wave. So microwave is for the communication between the tower and to the between the tower and to the devices or the mobile phones or the networks, and the millimeter wave is for the backhaul or short distance communication. Okay, so these are the two major bands of frequencies which are going to be used or for the full 5G network. Now, what are these frequencies? So that we are going to talk about. So that is sub 6 gigahertz microwave band. Sub 6 gigahertz means the frequencies below 6 gigahertz. So it is basically it is just above the. It is basically the frequencies below the 7 gigahertz are there. Just for the namesake, they have given the sub 6 gigahertz. Another are the millimeter wave. That is millimeter wave bands. And what they have decided to use, that is FR1 and FR2. That is frequency range 1 for the microwave range and frequency range 2 for the millimeter wave. So that is 410 megahertz to 7125 megahertz for the mobile communication, and for the backhaul or short distance communication, that is 24 to 52 gigahertz they have planned. So based on these frequencies, they have given some names of the bands, that is NR1, NR2 till NR95 for the lower microwave frequencies for different applications. Let's say, so for WiMAX application, for Wi-Fi application, wireless LAN application, for any device-to-device communication, they have given a lot of specific bands. Still, they are allotting new bands to this one, and each band is having the frequency. Each channel is having the bandwidth of depending upon its application, that is 50 megahertz or 100 megahertz. Okay. Now, apart from that, they have given the 4 bands for the high frequency, that is NR 257, 258, 260, 261 for the high frequencies, that is uplink and downlink they have given. Okay. Now the main challenge is that, first of all, in the mobile communication, we must have both the bands at the same time. So that I am not going to discuss here. I will be going to discuss how to design the antennas for these bands, or how to design the MIMO antennas, and what are the challenges in designing the MIMO antennas at these frequencies. Okay, now the technology options are realizing the antennas. So first is 2D technology. 2D technology means, so we have planar microstrip line. It is 2D or 2.5D planar structures, microstrip line. Then we have that is CPW, different types of structure. So they have advantages like they are compact, low profile, lightweight components can be designed on, and they require inexpensive fabrication. Apart from that, and the disadvantage are they have significant losses if we move higher in the frequency, especially at millimeter wave frequency. They have radiation leakage and they have undesired coupling because most of the structures are open, and they have limited power handling capability due to the presence of the dielectric material. Okay, now the another technology is the 3D technology or 3D structures. So there they have the advantage of low losses, good quality factor, and high power handling capability. But at the same time, they have disadvantage that they are heavy, they require expensive fabrication, which you require CNC machine for the fabrication, and transitions are required if you want to connect to the planar circuits. Now, the researchers in 2000 have thought that why can't we combine the advantages of this 2D technology and the 3D technology? So they have come up with a new type of structure, what is called SIW. It is a planar form of a rectangular waveguide. It is where the top and bottom walls of a rectangular waveguides are realized by the top cladding and the bottom cladding of the dielectric substrate, and the side walls are realized by a series of metallic layers. So this is called SIW. We can say that SIW, that is substrate ignited waveguide, is just a rectangular waveguide filled with some dielectric material. So it has all the characteristics of the rectangular waveguide and the some of the characteristics of the 2D planar structures. So it is a planar structure. It will have both characteristics of both the technology. Now, introduction to SIW technology. So history. So the work of this SIW was coined much later. Before that, there was a group as Japan, that is, they've given the waveguide line. They filed a patent in 1994, and they have proposed a parallel play waveguide which has similar characteristics of SIW. After that, they have given this development of laminar waveguide. Different names were given. But the main work, the major work started by the Kiu and his group in 2000 in the Canada. So what they have established this SIW transmission line. They have calculated its characteristic impedances, propagation constant, attenuation constant. They did all sorts of characteristics. At those times, the computers were just there, so they have done it by using the empirical formulas, and they are still valid now. And they have shown the way to design the new technology can be used for the design of the microwave components. And in the next 20 years, you can see numerous papers have been published, and they have been applied in the numerous microwave circuits and high frequency circuits for the design of filters, antennas, oscillators, and numerous SIW technology with some better characteristics. Now, there's some of the design parameters, SIW design parameters. What are the design parameters? So it is a rectangular waveguide. So it will have a parameter is width of the waveguide. It is mainly related to the cutoff frequency, that is a fundamental SIW technology. So as you know, the rectangular waveguide is having the cutoff frequency, the cutoff dominant mode is T10 mode. So it also supports the T10 mode. Basically supports T10 mode, and the diameter D of this, whatever this via holes or the metallic via holes are there, and the longitudinal spacing between this via holes. Now the typical choice to just have the identical implementation of sidewalls. So that is S equals to D, but ideal value is S equals to D, but the typical choice is S equals to 2D. Means what has been found through the numerical simulation or EM simulation, that if we choose S equals to 2D, that is separation between the vias equals to the 2 times of the diameter of the vias, then there will be the electromagnetic field will be confined in this structure, and then it will flow. There won't be any leakage from this structure. Okay, now SIW. So as I told you, it supports TEM0 mode only. It doesn't support TM mode, because TE mode, TEN modes have the for the support of TM mode, it requires longitudinal direction, sidewall, this direction, Z direction current. So since it is discontinuous along the Z direction here, along the sidewall, so there is a discontinuity. So it doesn't support the TM modes. It only supports TEM0 modes only. Okay. Now these are some of the design formulas, means cutoff frequency. So now these are the sidewalls are there. So if we replace the sidewalls, then they calculate the W effective basically because of the replacement. So here the effective formula was given. Again, it was calculated empirically, and they have provided this structure. They have provided something like this design graph is there. Means it is not like that you can choose any value of S and D, that is spacing between the vias and the diameter of vias for the propagation of electromagnetic wave. So it is the region blue here is shown will be only of region of interest. Other region is either it is unrealizable or the region of loss or band of rejections. So only this region. So S by lambda C and D by lambda C has to be chosen only in this region for the proper propagation of electromagnetic wave in the SIW technology. SIW, that is substituted waveguide. Now, as I told you, for any transmission line, what we require the propagation constant, characteristic impedance, and the alpha, basically gamma and Z naught. So the group at Q has calculated the numerically. So so they have find out that for two modes, that is TE10 and 20 modes, it is similar to the rectangular waveguide, and the characteristic impedance is also similar to the rectangular waveguide, and they have shown basically it is a design chart which can be used for the design of the microwave components. Okay, now, so it is something like it is in between. Means if we compare this SIW, that is substituted waveguide, with other guiding structure, that is coaxial line, metallic waveguide, strip line, microstrip line, coplanar. So it is in between it has neither the advantage, it is not as good as a metallic waveguide, not as good as strip line, but it is in between. Means it is better than the 2D planar structures and somewhat inferior to metallic waveguide, but at the cost of ease of fabrication, and somewhat higher power handling capability than the other 2D structures. Okay, so that is why it is more popular nowadays. So now, so this is one of the transmitter they have designed, or they have just shown how SIW, the entire thing is basically antennas, couplers, and antennas, couplers, and they have oscillators. Most of them are using the SIW technology, and this is and if you want to use it, so you have to apply certain chips for signal processing and for down conversion, and so this is SIW based a transceiver will look like. So now we have to understand how does to design the SIW antennas, couplers, filters, and so on. Okay, so I have discussed about the advantages and the limitations. So these are some of the components which our group has designed. So we have designed some of the planar structures, planar antennas, 3D antennas we have designed, and planar filters we have designed. So now we will discuss the SIW antennas. So before starting, so that is rectangular SIW cavity. First of all, I will discuss. So what is rectangular SIW cavity? So you know a rectangular cavity basically, or cuboidal cavity basically. So it is a cuboidal cavity. So it will have X, Y, Z. So it will resonate at some frequency, that is TE. The dominant mode is TE110, 100. So similarly here also we have similar dominant. So what happens? This is a rectangular waveguide cavity. So we have the how it is formed. So we have the same SIW technology. If we close the front and the back side of this one with another metallic series of vias, so we will get a cavity. So this cavity will equivalent to the rectangular cavity. In the same, it will have all the features, all the formulas can be applicable. Only the difference is that, so here the length, earlier it was LC and WC, now it has been modified to L effective and W effective. This L effective and W effective are calculated empirically. So they have calculated for different substrate parameters and different heights. So they have come up with some empirical relations. So if we use this relation, then we will get the correct formula, or the correct resonant frequency of our this SIW structure. Okay, now this was our rectangular SIW cavity. So this is act as a microwave resonator, which we will be using for the design of antennas and filters. Now feeding to the SIW, so the main thing is that if you have any structure, you have to launch the power. So how you launch the power? So there are different types of feeding techniques are there. So first of all, because this is at this side you will have 50 ohm, and at this side you have the impedance of the waveguide, whatever the mode you are choosing. So you have to match this impedance and this impedance. So a taper transition based is used. This is much popular being used. This is one of the simplest transition. Apart from that, the coplanar to SIW transition, where the current probe is being used, and another one is the coplanar to SIW with 90-degree bends. So here also you have the 50 ohm. Now to match the 50 ohm to match to this one, so a 90-degree bends are used. So there are different types of, basically you have to match the fields of a feed line to the SIW in order to launch the power properly. It should not reflect whatever the power you are launching. It should not reflect back. It should go inside the waveguide. Okay, now, so people have presented different other feeding techniques. Now, other feeding techniques there, that is single feeding, then double feeding, offset feeding, then double quadruple feeding. Means all have, one of them have advantages, one of them disadvantages. So as I will discuss, when I will discuss some of the components, I will discuss what type of feeding techniques you should choose. Okay, now, so first of all, we should study the modes of the SIW technology square cavity. So now this is your SIW square cavity. As I have shown you the rectangular waveguide cavity, so it is just a square. Its 2D view is something like this. So and 3D isometric view is like this. Okay, now 2D view. So here I have plotted for this dielectric substrate first few modes, that is TE110 mode. So basically it supports, as I told you, TE MN0 mode. It will not support TM mode because the waveguide walls are, means this is not, they are discontinuous, it will not support TM modes. Now, so that is the, so TE110. So one first index shows the number of half wavelength variation along the x direction. Second index shows the number of half wavelength along the y direction, and 0 shows the third index shows the number of half wavelength variation along the z direction. So now in nomenclature, if you see, this is your x, so it has one variation along the x direction, and along the y also it has one variation, and there is no variation because the thickness is very small. H is very small compared to the other dimensions, so it is no variation of the fields along the z direction. So that is why TE110. Similarly, TE210, it will have something like this. It has two variations along the x direction and only one variation along the y direction. So in the similar way, TE120 and 220, where the positive sign shows the fields in the upward direction, negative sign shows the fields in the downward direction. It is shown here. So it is just a 3D view of the whatever the fields here. Similarly, here, here, and here. If you see the TE220 mode, it has the fields like this, plus, minus, and also the no two adjacent fields are having the same sign. It can be visible when you use this components, then we will see that also. Now, SIW is slot antenna. So first I will talk about the slot antenna. So what is a slot antenna? A slot antenna is basically a metal surface, usually a flat plate in which more holes or a slot or different sizes are edged or cut. Okay, now this slot will radiate. It will act as a dipole. Go back and study what is Babinet principle. A slot is act like a dipole. So if you it is written that so similar way as a dipole antenna. So it will have all the omnidirectional radiation pattern. Only the plate is there. Okay, so it will have all the omnidirectional radiation pattern and the pattern of 8 in the in the two planes are there. Now, so this slot, the shape and size of the slot determine its resonant frequency, whatever the operating frequency of this antenna. Now, this slot has the main advantage that it's very simple and you can design it either in the wave planar structure. It's just a plane, you just take a sheet, it will radiate. But the disadvantage of this slot is that you have the radiations at both the ends, front and the back. Now, if you want to design the direction antenna, it should radiate only in one direction. That is why this slot has been modified with a cavity, a solid cavity is kept behind it. So that is called cavity backed slot antenna. So now here, this cavity is of the λ/4 thickness because it is shorted here. So it should not get any load to the slot because it will be λ/4 is shorted. So it will be act as an open circuit here. So this will be acting as a radiating slot. So now when you excite this cavity of the particular mode, this slot will radiate. Now the advantage of this is cavity backed slot antennas, they have very high radiation efficiency, very high front to back ratio, and since this structure is closed means from the side, this one, so it has the good isolation from the environment. Okay. Now, if I implement these things into the SIW technology, think of, so these side walls of this cavity are realized by a series of metallic vias. So you will get cavity backed SIW based slot antenna. So it is low profile, cost effective, simpler design, and easy of integration with the planar circuits. Now, the cavity backed slot antenna, here are the numerous you can find in the literature, maybe more than different types of slots. So just the theory behind everything will be remain same. You have to excite the particular mode of the cavity, and you can feed the cavity an HA slot, and this slot will radiate at the desired frequency of this one. So here they have taken the rectangular cavity, they have taken the square cavity, and they have taken the circular cavity, and different types of slots are edged. So the theory is all the same. So I will just, so what is the design flow chart of this one? So you have to choose the cavity, then you study all the modes of the cavity. Means so SIW will have different modes. So as I told you, I have shown you T110, 210, 220, and all the modes are there. So depending upon the modes, so you have to first see the cavity and then see the mode pattern and how the field configuration of these particular modes are there. Then you apply, this structure will support the modes, then you apply the feeds to excite the particular mode, then place the radiating slots at the strategic location. That I will tell you how to do that. Then finally this slot will radiate and you will get your cavity bagged slot antenna, and you can get it for the different dimensions, impedance, bandwidth, polarization depending upon the requirement, and finally you fabricate it and you will verify the characteristics. So this is the design flowchart of your cavity bagged slot antenna. Okay. So I will take this one starting with the cavity bagged slot antenna. This is simplest one. So as I told you, so this is the simplest one. Okay, so I will be using my whiteboard here now to explain you. So this is simplest one. How to, the question comes, so where to edge the slot and all these things. So let me show you something. Okay, so my board is visible.
Yes sir, visible too.
Okay. So now as I told you, TE110 mode. So you have TE110 mode. So this will be, fields will be like this. So fields will be like this. So it will be plus. Now you can feed from any side, either this side or this side, this side, this side. And if you feed from this side, so this mode will get excited. Okay. Now if you etch a slot, if you etch a slot at the center location means this one, then will it radiate? No, it will not radiate, because these points are having the equipotential. Now if you think of your capacitor, in the capacitor, if it is positively charged V0 and it is grounded, so then the fields will be like this. So it goes from the higher potential to the lower potential. In the similar way, if you see the electric fields here, the electric fields are having the equipotential, means the potential will be similar across. Now if I etch a slot somewhat offset here, maybe here at this location, then what if you see, if you observe the potential at this point and this point, it will be different. So where as I told you, the higher potential to lower potential, so it will move like this. So you will have the radiation along this direction. So this will give you, the radiation along the, let's say this is your Y. So Y polarized electromagnetic wave will be radiated from this slot antenna, whatever I have shown you here. Now, so it will be using only TE110 mode, the first mode, and this length will be your lambda G by 2, because it is shorted at one, that is short circuited here, so you know the length between the two short circuit is lambda G by 2, so it will be lambda G by 2. So its bandwidth is very less. If you see, the bandwidth is very small here. The bandwidth is around 1.7%. Now another is that, so we want to increase the bandwidth. So what we can think of, we can use the higher order modes. How to use higher order modes? This I will discuss you. Higher order modes, if you choose. So here they have used TE110 mode and TE120 mode or TE210 mode. How to do it here? So if you see the fields of TE210 mode, that is 210. So 2 is something like this. So 2, let's say I will take you 120. So you will have fields like this. So like this and this. So this is plus, this is minus, and this is TE110 mode. TE120 mode. Now the here plus. Now the question comes. So if you feed from this side, this mode will getting excited. This mode will also get excited. This side, both the modes will get excited. But if you feed from this side, this mode will not get excited. Why? Because this is having the zero fields. It is having maximum here, then zero, and then minimum. So it will not get excited. So you have to feed from either this side or this side. Now if you feed from this, either this side and this side, then both the modes will get excited. Now both the modes will get excited, so we'll have both the modes. So we will feed like this side, either this side and this side. Okay, now so we'll have, that is this mode and this mode, both the modes will get excited. So plus minus. Now the question comes, where to etch the slot? If I etch the slot at the center, will it radiate? It will not radiate, because as I told you here, it will not radiate because it will have the equipotential. But if I etch the slot here, then what is going to happen? It will radiate because there is a potential difference is there. So as I told you, the positive to negative, so it will radiate, but it will not radiate. But if I etch a slot at any other location, let's say I etch a slot at this location, then what is going to happen? Both of them will radiate. Why? Because here you will not have the equipotential surface, it will radiate, so you have the potential difference. Also you will have the potential difference, so both the slots will radiate. So this works. They did it here in the second example. So it is somewhat they have taken offset from the center. And one more thing, they have made the cavity rectangular because they have made the cavity rectangular to bring the second mode closer to the first one. So to bring the second mode first to earlier, let's say if you are first, that is if you are earlier, what happens? TE110 mode is here and TE120 mode is here. So now, so as you know the formula of TEMN0 mode, it is something like what happens? So it will be m pi by 1 over something like m pi by A n pi by B plus p pi by C is whole square. Now, so ABC, so ABC is your basically H. A and B are the dimensions. So A and B are the width of the width, that is WC and LC of a cavity. So now if I choose in such a way that if I choose means this mode will be brought up closer. Because if you choose that is width is much, if you choose the width of a waveguide longer, then this much will be brought closer to each other. So it will become 1 to 0. Now this modes can be emulgated and you will get the wideband response. So here in this case they got the bandwidth from 1.7 to 6.3 gigahertz. So the bandwidth has been improved from 1.7 to the 6.3 gigahertz. Another is they have designed the SIW. So this is much broader. So as you know, the butterfly shaped structures are known for their wideband characteristics. So it is basically butterfly structures are wideband structures. So what happens? So you have the butterfly. So something like this. It is basically you are etching multiple slots of different length. It is basically, so first they will take this length, means broader length, then shorter length, and so on. Means it will be just a wideband structure. So you will get the wideband characteristics. Okay. So now, so these are some of the SIW slot antenna. Now, how to use this slot antenna for the design of the MIMO antenna that they have shown. So the SIW MIMO antenna. So this is the simplest one in 2015, that is Zn Chen has presented. So they have just straightforward introduced at the center and they have center fed it, and they have kept like this. 4 different type cavities are there and they are kept side by side, and they have applied the orthogonal polarization such a way the isolation between them will be small. Now apart from that, what they did, they have applied something like metamaterial based structures. So they have calculated its propagation constant, that is structures metamaterial. So this metamaterial structure shows that they have calculated its omega beta diagram, and they have find that it is having the band gap characteristics between, that is they have basically designed antenna for the 2.4 gigahertz, and they have designed this band gap structures such a way that its band gap lies at 2.4 gigahertz. So there won't be any flow of electromagnetic power from this side to this side. So you will have the better isolation between the MIMO antenna will be observed. Okay, now so this they have shown here. So they have got very good isolation of 42 dB, and the edge to edge gap is only 2 millimeter is there, very small, and it is similar to the whatever this they have designed the And another one, they have given the basic thing is that you have to obtain the isolation structure. Now this is another structure they have obtained by placing different types of VRs, but it was having the much larger dimension, that is the S to S gap is 5 centimeter for the 5 millimeter is there, and again they have placed it by placing something like some discrete mushroom shaped structures are there. So I'm not going to the discuss details of this. So they got some isolation of 25 degrees. Now another one from the Kundan itself. So what they did is they have used some half mode and they are kept side by side in such a way they applied the orthogonal feeding structure. Also, so they also got the isolation better than 24 dB. In all the above structures, as you see the 34 and because they have applied some decoupling network type of structures, mushroom like structures and something like some band gap structures are applied, and they have got it. Now another is that miniaturized SIW. So this is my third section of my talk, miniaturized SIW antenna. So what do you mean by miniaturized SIW antenna? So all these modes, if you see, all are using the full modes. Full modes means you have the full SIW cavities are there for the design of the SIW antennas. Now the several miniaturized version of the SIW antennas are there, so which are used for the design of the that is MIMO structures. So what are they? So I will discuss here. So we have the circular SIW cavity whose dominant mode is TM010 mode. Now this is your full mode. Now if I apply the that is magnetic wall concept, magnetic wall means it is open circuit concept, then what happens? If the any fields are symmetrical around any plane, if you apply the magnetic wall concept, then you can bifurcate or reduce the size of the structure by half by retaining its characteristics. Resonant frequency, everything will remain same, so size will be reduced to half. So this is called half mode SIW cavity. So it is something like semicircular cavity is there, so half mode. Similarly here, if I bifurcate along here, you can bifurcate, first cavity is bifurcated along any plane here, so you get half mode. Now if I bifurcate along this, basic thing is that you have to bifurcate along the symmetrical plane. If you apply bifurcation here, so you will get the quarter mode here. Similarly 8th mode, 16th mode, and so on. This is circular cavity bifurcation. Similarly, you can think of the bifurcation in the SIW cavity, whatever I have discussed. So the full mode is there, half mode, quarter mode, 8th mode. Similarly, this is bifurcation along the center. If you bifurcate along the diagonals, so you will get something like this. So this is half mode, quarter mode, and EMSW. So if you can see all these structures have the similar characteristics, but size will be reduced to half. Now this comparison, if you compare with this one with the others one with the SIW structures, the size reduction in the 16th mode or whatever this modes, if you have full mode cavity, it is 0%, is similar. Now half mode 50%, then if you see the significant size reduction is obtained. And also if you observe the quality factor of these things, so it is having the similar, more or less, not much degradation in the quality factor. If you have full mode is having the cavity of 200 something, it will have the 175 and something like that. So basically it is somewhat reduced, but the size will be drastically changed. But there are several methods you can increase the quality factors. Quality factors are there, are supported in the literature. Now this is the first of all this miniaturized SIW antenna, the square SIW cube SIW structure. So this is, so if you fed from the side walls, from any of the sides of the, so the TE, whatever the TE110 mode and TE220 mode will be getting excited, and you will get the two dual band structures or dual band antenna can be designed here. Now if you see the circular SIW cavity, then what is going to happen? In circular SIW cavity, the quarter, that is, this is quarter mode and this is 16th mode. So if you fed from the, here they have fed from the coaxial fed, and so what they got, circular SIW antenna radiation characteristics are there. So these are the, now we can use this type of antennas for the design of the MIMO antenna. So the miniaturized SIW antennas for microwave, that is this one, MIMO antennas. So now first example is shown here. So here they have taken the two QMSIW cavities and they have coaxially fed, and they have applied a decoupling structure here decoupling structure, basically the side walls. So to get the isolation, good isolation, so they go about the isolation of 18 dB is obtained. 18 dB is obtained here, and uh, obtained. And another one there, it was 2 cross 2, means 2 port MIMO structure. That is for the 5G MIMO antenna. They have realized that is. Now another is they have for high order. They have applied this one, the 4 type of, that is 4 QMSIW structures. So now if you see this structure is much more simpler or much more compact than the full mode structures whatever have been presented earlier. But isolation is somewhat poor, but there are again different methods by which we can enhance the isolation. 20 dB isolation can be easily obtained by etching the slots or by placing the VRs. Means VRs can be done. Okay, now so here they have placed 2 similar structures like this and this one. So now they have used the 8th mode, further 8th mode, and the isolations of nearly 18 dB has been obtained. Now after that, this type of structures means numerous type of structures they can use, and it is up to you how you place this structure to get the polarization diversity or pattern diversity, to get the enhanced isolation. Now here they have used the square MSIW cavity to get the isolation. So, and here they have fed from these sides. Okay, now in circular SIW cavity, so they have used the circular, they have placed side by side, and beneath they have HA isolation. They have HN slot beneath it. Okay, the 4 pole and so on. So they have used 16, sorry, 8 or 12 antenna, 12 port MIMO antenna for the design of the, again for the mobile applications. Okay. Now if you have any questions, you can ask me, then I will progress further. Yes. Yeah. Questions?
So, any questions from the audience participant side? So, okay, sir. I think you can continue. We will take the question in last of the session.
Okay. Okay. So now, as I told you, the SIW, only 5 to 10 minutes are left. So you can just 5 minutes are left. So SIW slot, and that is antennas for IoT applications. IoT, that is Internet of Things of applications, means if you see here, for IoT application, Internet of Things application, your materials should be environment friendly, because we are going to be used in bulk, and it should be green and recyclable. So what people have used it, the organic materials, such as cork. They have used cork, or they have used the leather, or some textile is used for the design of the antenna. So they have used this cork structure is there. So, and for the top, they have used something like the conductive copper, some polymer is there. So they have used, and the side walls, they have used the ripets are there. So they have used it. So they have designed a cork based SIW based antennas. So where they have used cork as a structure, and leather, means they have used fabric substrate, cork substrate, and leather substrates are there. And one more thing, so what you have to do before designing any structure, let's say you want to design this structure, you must know the characteristics of what are the materials are you going to use. That is, you have to calculate its characteristics. So there are different methods by which, that is Nicholas-Ross method is there, by which you can experimentally calculate the material characteristics, permeability, and the tan delta of the material. And if you know these things, then it's straightforward. You can use it for the design. Okay, so they have used some textile-based materials for the design of the SIW antenna. Everything remains same. The principle remains same. They have apply all whatever the modes, T110 mode, feeding, only they have replaced with some user-friendly technique, user-friendly materials. Also, so since this means if you apply for the body area network, or maybe for any application, so whatever this will be bend up. So you have to calculate its means how does your antenna behaves in the bending, means if it is bent, because let's say here is a firefighter is shown. So if I apply on his hand, on his hand, so you have to find out this characteristic. Means while designing, you have to take care of the bending of this. How does this bending affects the radiation characteristics of the antenna? You have to take all these things into the account while designing. Okay, they have designed the, again I said to you, the cork based antenna. So I will stop here. So if you have any questions, you can ask me. Yeah, they have designed the paper based also.
Okay. So now house is open for the questions. So dear participant, if you have any query, any questions,
yeah,
you can ask Mr. Sir.
Sir, can we get the PPT of this?
Yeah.
Yes, Saurabh.
Sir, can we get this PPT?
And you can get the PPT, no problem. I will share you.
Okay, sir. Thank you.
Yeah. Questions?
Good morning, sir.
Yeah.
Thank you for your nice presentation, sir. I have some doubts related to fabrication of this antenna.
Okay.
Mostly, sir, you stated in the paper-based antenna, or the material like cork or leather can be used. Can you tell us how this antenna will be fabricated if you use paper or this leather substrate?
Okay, paper.
Yes,
so,
sir.
Okay. Paper, see, it is something like this. They have. I have not done it. So it is something like copper tape is there. So in the market you will get the copper tape. Okay. The paper. First of all, first thing is that you have to characterize the paper. So paper it can be hardboard or it can be just a thin paper. Let's say, because if you take some hardboard is there. So calculate its permittivity and permeability. Okay. So by the method I have discussed, so by the, as I told you earlier, so this is the method, that is a resonance perturbation method, or just simpler method is make a cavity, put the material in the cavity, tightly filled it, and measure its change in the S parameter. Generally we do the experiments in the BTech. So you calculate the characteristic, you calculate the epsilon R and the tan delta of the material. Any material can be easily calculated. Okay.
Okay, sir.
Tan delta and the epsilon R of the material. Once you calculate these two things of the material, that is loss tangent and then you use these things while designing your antenna. Okay. Now while designing your antenna, now the copper tapes are available. So simpler copper tapes are available in the market.
Yes, sir.
Copper. You can go to the Google, Amazon also. You can find out the copper tape.
Yes, sir. Yes, sir.
Simple copper tape. If you see, it is visible. So the copper tapes like this are available, and you whatever the PCB fabrication technique you use, you apply these things on the PCB or any other material and try to do the chemical etching as done by this, because we don't do it. Here lab is there, so they perform the chemical etching. So if you do the chemical etching of this copper tape and then you apply on the paper and connect the connector.
Okay, sir.
Okay, then the paper antenna can be made. In this way, this is the way by which the paper antenna can be made. And in similar fashion, either you can make it the cork based or the variable antennas in similar fashion. So here they have used, in the literature, if you see, they have used some fabric. So fabric, they have, their fabric is being used, and you can use this fabric for characterize the material. Then you get the result. You get the epsilon tan delta of the material. Then you do apply this thing tan delta and this one epsilon in the design, and design the antenna and get the fabric, get it fabricated.
Yes, sir. Sir, one more thing. Can we call them as a flexible antenna?
You can call it flexible antenna, no problem.
Yes, sir. Yes, sir. Okay. Thank you,
Yeah,
sir.
you can call this as a flexibility, no problem. Because unless you can, and one more thing, you have to design. If you want to apply these things, so you have to apply. You have to do this analysis, whatever I have talked about. This analysis.
Yes,
So
building analysis.
analysis, how does it? It is when it is flexible. When you are going to apply this thing on the some structure, and then how does this radiation characteristics will change?
Yes, sir. Thank you, sir.
Okay. Yeah.
Any other question from participant side?
Okay. How many of you working in the antenna domain? I am seeing 70 near about, so maybe participants. Maybe how many of you working in the antenna domain? Okay. Okay. Any other questions?
Any questions from participant side? So, sir, I think there is no question
Okay.
from the participant side. So we will conclude this session.
Okay.
So, on behalf of the organizing committee and the participant of the short-term course at NIT Jalandhar, I extend your sincere gratitude to you for gracing us with your presence and sharing your expertise as the keynote speaker, sir. Your insight keynote address not only set the tone for the entire course but also provide us with the profound perspective on the topic of substrate integrated waveguide and their applications for the future communication. Your deep understanding and clarity on the subject were evident throughout your presentations, leaving an incredible impact on the all attendees. We greatly appreciate the effort you took in the meticulously preparing your speech, which resonated deeply with everyone present. Your ability to blend theory with the practical example made the complex concept accessible and inspire all of us to delve the deeper into the subject matter. Furthermore, your willingness to encourage with the audience during the interaction sessions enrich our learning experience and first a meaningful discussion among the participants. Once again, I thank you, sir, for joining us in a very short invitation period. Your presence truly has been highlighted our learning journey, and we hope to have the opportunity to welcome you again in a future in a physical mode. So thank you very much, sir.
Thank you, Kundan.
Thank you very much, sir.
Yeah. Thank
So,
you.
sir, I think if you have interested, then you can leave, sir.
Okay. Thank you. Yeah.
Okay. So, dear participants, now this session is over. So now our another session, which is lecture come hands-on on the microwave component at 11:30. So I request to all you all are join the sessions on 11:25. So thank you everyone. Either you can wait here. So thank you everyone. Yes, Kailash sir, I think you have raised your hand.
No, sir, I raised that. Sir was asking about who's working in antenna. In that regard, I raised it.
Okay. Thank you, sir. Okay, thank you, sir. Good morning, sir.
Yeah, good morning. I'm audible.
Yeah,
Yeah, good
sir, you
morning.
are audible.
Good morning.
So, shall we start, sir? Yeah, we will wait for 1 or 2 minutes.
Yeah, absolutely.
Okay. Hey, do I have to join here? So, I think without wasting of any time, we will start the session. So, in this session, with us, Dr. Avinash Chandra, sir. So, Dr. Avinash Chandra is working as assistant professor, associate professor in the School of Electronics Engineering, VIT Vellore. He received PhD in Electronics and Communication with a specialization of RF and microwave from IIT ISM Dhanbad. His PhD involved in design of planar structure embedded multiband waveguide aperture antenna with involved radiation characteristics. He has published more than 40 papers in leading journals and conferences. In the last 5 years, he has published number of quality paper in the area of waveguide, shielded aperture and polarization configurable in the reputed journals like IEEE, Transaction Antenna and Propagations, and etc. He is the potential reviewer of the many journals and conferences such as IEEE Antenna and Wireless Propagation Lectures, IEEE Transaction Antenna and Wave Propagations, IIT Antenna and Wave, International Journal of Antenna and Propagations, and International Journal of RF and Microwave Computer Aided Engineering. His current research area is waveguide reconfigurable arrays, antennas, and microwave components for 6G applications. So, with the words, I would like to invite our expert of the sessions, Dr. Avinash Chandra sir. Over to you, sir.
Thank you, sir. Thank you for the introduction. Uh, so first, let me share the screen. So right now, I'm going to share the entire screen. So just you can tell me whether it is visible or not. Kundan sir, PPT is visible.
No, sir, screen is not shared.
No, no, no.
Please share it.
Okay, okay. Just I'm going to window tab. Now it is visible.
Not here, sir. Yes, now it is here, sir.
Okay, okay.
Yeah.
So,
Now it is visible.
yeah, good morning to all. I am Dr. Avinash Chandra, working as Associate Professor in the School of Electronics Engineering, VIT Vellore. As Professor Kundan given the nice introduction. So, today our discussion basically we are not going to explain the theoretical part because this session is the hands-on session. So, I will give you short idea about the waveguides. So our talk basically concentrated on the design of waveguide components for the X-band 5G millimeter waves or beyond application using microwave studio. So actually, if we are talking about the high frequency, so we have multiple choice like planar antennas are also there, but if we are talking about the high power applications, so we have only one choice, that is the waveguides. So in this talk, because this is the hands-on session, so I am going to design within next 1 hour. So different type of waveguides like slotted waveguide or twisted waveguide, aperture array. You know that the basic things like T's, couplers, and if time permits, we can design also the planar antennas for the uh, different applications. So first, I will give you some basic idea about the waveguide. Then directly we'll go within 10 to 15 minutes. I will give you the basic idea. So how you can design with the any software, as actually we have a multiple numerical software available for the designing of antenna, coupler, or waveguide components, or maybe microwave components like CST Microwave Studio. Second one is the HFSS. Then AWR is there, PECO is there. But most two softwares are popular among the RF researcher. One is the CST Microwave Studio, and another one is the HFSS. So these are the outline of my presentation. So basically, waveguide is nothing. It is a guided structure that can guide an electromagnetic wave. So waveguide is going to be used for a high frequency because they have the larger bandwidth and lower signal attenuations. So if you are going to design any waveguide, so for a in the microwave, we have a different bands like L, S, C, X, KU millimeter waves, and so for each and every band, so waveguide dimensions are going to be fixed. So we are not going to change the dimensions. Let us suppose that for if I am going to, that is a most popular waveguide, is a X band wave.
Sorry to interrupt you, sir.
Yes,
Right
sir.
now you are in which slide?
Second number slide.
So I think slide is not moving, sir.
Slide is not moving.
Yeah.
Okay, sir. I'm going to stop.
Yeah. So better you can share the entire screen.
Okay, okay, sir.
Then actually this is the movie.
So now is this slide.
Yeah. It is now it is moving.
Okay, and confirm this one also CST.
Yeah. Yes, sir. Yes, sir. It is also moving.
Okay, okay, thank you.
Oh, thank you.
So these are the different waveguides like metallic waveguide, circular waveguide, or twisted waveguide. So these are some examples of the waveguide. So uh, where it have a applications like we have a slotted antenna. Basically, we are going to find in the radars and why, because it have a very high gain, high power handling capability, low loss, and easy to fabrications. It is capable to give vertical and horizontal polarization. So in the researcher, so they have different doubts like uh, right now everyone is going to be work on the planar antenna. So why we are going for the waveguide? So just 2 weeks before, I visited in microwave tube. That is the lab of DRDO. That is a dedicated lab for the making the clastron tubes and waveguide components. So they are asking everyone is going to work on the terahertz antenna. So we have the discussion with the scientist. Santanu is there. So as per discussion, they are asking like we have to design the a slotted waveguide antenna that have a very high gain, like high gain in the terms of like practically we have to show a gain of 45 dB, and it is going to be like we are going to generate the power of 100 kilowatts, right? So practically, it is very difficult to get a gain of 45 to because they are asking the practical aim. So if you are going in the simulation, so at least we have to maintain a gain of 50 dBi. So it is very difficult to get a gain of 50 dBi from any like planar antenna or any type of planar structure. So we don't have any options, or maybe the audio also they don't have options. So only one thing is the waveguide is there. So how we are going to design this? Design constraints are given. So within couple of minutes I will explain each and everything. So if you see like where it is going to be application. So if you are going to the airport or a submarine radar, so in the submarine radars also we have the waveguides, that is a slotted waveguide is there. So I have taken this picture from the internet. So that is that slotted array. It is a radar is there that is going to be used in the submarine ship. Other applications like we have a anti-ship missiles. There also we have a slotted waveguide. Uh, Coming to the military and defense applications, so in the waveguides wings, there is some steepness structure is there. Also the radar, they are going to communicate with the radar. So that steepness type of structure is going to be embedded uh, in the wings of the aircraft. That is also it is going to be used as slotted waveguide, like parabolic reflectors are there, or anti-tanks missiles are there. So everywhere it is going to be used. These are some examples that military radar station in the Thailand they are going to use a slotted waveguide. In the Antarctica also they have placed a circular waveguide, and inside that slotted waveguides are there. So everywhere it is going to be like especially in the defense purpose, or maybe for the radar or setcom applications, the waveguide components is going to be used. Either uh, antenna is there, or filters are there, or maybe couplers are there. Maybe complexity and designs are going to be different depending upon the applications. But if I'm going to conclude the applications, so basically the waveguide have mostly application in the defense sector, or maybe the or radar or satellite communications. So we have designed different types of waveguides. Just I am going to scroll because this session is a hands-on session. So I will design all the waveguides one by one, right? So these are the circular coaxial type of circular waveguide. It is going to be used for the millimeter wave applications, and you can observe here the 2000 elements of slotted waveguide. It is going to be installed in the Hiroshima Institute of Technology. That is going to be used for the surveillance purpose. Another type of waveguide, that is a grouping structure, is going to be added. Recently, it is going to be published. So, like in the 5G technology or millimeter wave technology, the concept of gap waveguide is going to become right. So, the different research groups are going to be designing different type of slotted waveguide antenna, like a waveguide having a groove structure, or maybe a waveguide, or maybe a gap waveguide technologies are there. So they are going to design the antennas or filter for the 5G application. So now I'm going to share, because this session is your complete hands-on session. So I'm going to share a basic how to create the project in a CST. So first 5 to 10 minutes I will I will explain through the PPT. So how to create the project, and then directly we'll go to the CST to design the different type of antennas, filters, and couplers or magic T with the help of CST Studio. So in the CST Studio, like supposed to be, if you are going to design any waveguide component, so first target is there, where we can use. So what is so which applications we are going to design, whether you have designed any antenna or any filter for a Bluetooth applications or for ISM band, or maybe for the X band applications, for the radar, for the satellite. So depending upon the cost, you can choose the frequency range. So initially, if you are going to open a CST, actually we have a two software. One is the CST, another one is the HFSS. So basically, HFSS is going to work on the finite element method, and your CST, computer simulation technology, microwave studio, that is going to work on the finite time difference time domain, right? So if you see the working space of HFSS, no need to select any template. But in CST, why we are going to select the templates? So in the upcoming slide, I will tell you what is the reason. So first, you have to create a project. Like supposed to be, you have, whether you have to design the antenna, whether you have to design the, you have to design a periodic structure, or whether you have to design a filter or coupler. Based on that, first you have to create a project. In the project template, actually in the CST studio, it is customized is there. So for antenna, because boundary we have to put the boundary conditions. So in the CST, no need to select any boundary condition. So first you are going to create a project. So this type of window is going to become, right? So whether you have to work in the microwave, or whether you have to work for the EMI/EMC, or maybe low frequency, or for the optical application. So our this in the today's discussion, basically we have to design a microwave component. So we are going to select the microwave. In the microwave, either you can select the antenna or circuit component. Let us suppose that you have to design an antenna. So I'm going to select a antenna. So once, let us suppose that in our PhD duration or MTech duration, our supervisor fixed the title, whether you have to work on the antenna, whether you have to work on the filter. So once you have created the template, then again no need to create the template. Let us suppose that your research domain is going to be moved. Let us suppose that someone is going to, right now it is going to work on antenna, and he is going to be move on work on the filter or coupler. So again you have to create a new template. Otherwise, if you already define the project template, that is going to be listed in the your window. So once you have selected the antenna, then click on the next. So in the antenna, different type of antennas are there, like waveguide, planar antenna, wire antenna, phase array antenna, RFID antenna, or mobile for mobile phone. We have the antenna. DRS are there, or RFIDs are there. Let us suppose that depending upon your working research area or your research area, you can select either waveguide, planar antenna, RFID, or DRA. Click on the next. So it is going to become, you have a three type of solver. One is the time domain solver, another one is the frequency domain solver. So generally, actually, you can select either time domain or frequency domain. For we are work here, we are going to work. We need the rapid result. So we are going to work on the time domain. Let us suppose that if you are going to select a frequency domain, so mesh cells are going to be more. In that case, your iteration is going to be like, it will take the time. So generally we are going to select a time domain. For generally filter and other waveguide components, for antenna, it is okay to select a time domain. But supposed to be, if you are going to work on the components like filter, or maybe you are going to work on the couplers or magic key, so you can select a frequency domain analysis. Once you have selected the solver, then you can create a project. So you have to choose your dimension in the millimeter. Right now, supposed to be someone is going to work on the terahertz or 6G communication. So you can select the dimensions like in the micrometer, same in the frequency like terahertz. So we are working on the X band or millimeter wave. So we are going to select the gigahertz, right? And once we have selected the dimensions, then click on the next. So after that, it is going to be asked whether it is going to be finished. Supposed to be, if you are done some mistakes, you just go on the back on the project template. So once you click the finish, your template is going to be created. So you can see that this is a user interface of the CST. Now supposed to be, I'm going to take a general example. Let us suppose that you have to design a planar antenna, microstrip antenna, that is going to work on 2.4 gigahertz, or maybe 9 gigahertz, or maybe any operating frequencies there. So for that one, what we have to need? First, substrate material. So material may be, your substrate material may be FR4, or maybe Rogers, or maybe depending upon the application. Like you are going to work on the variable application, so maybe material is the jeans. Next one is the, in any antenna we have a three things. One is the ground plane, one is your substrate, and one is the radiating patch, right? So this these things are going, we have supposed to be, if I'm going to take is normal patch antenna, what we have to think: one, what material we are going to choose; next, patch, that is a radiating element; then substrate, what is the dielectric constant. Let's suppose that you have a part material, so you, that is easily available, so you know that the dielectric constant is 4.4. Then ground plane is there and connector is there. So here also different feeding techniques are there, like microstrip feeding techniques are there, and CPW feed techniques are there, coaxial feeding techniques are there. So here for the illustration purpose, let us suppose that I am going to take a coaxial feeding technique. Now important thing is there, let us suppose that for any RF or microwave component, first you have to decide on which frequency you are going to work, right? So in the waveguide, mathematical calculations are there, but in planar antennas, some heat and trial methods are there. Everyone is going to be some mathematics is also there, right? So first you have to select the operating frequency of any antenna, any filter, or any coupler. So once you have selected the operating frequency, then you can design. So for the tutorial purpose, for this PPT, we have selected the operating frequencies 9.4 gigahertz. Now coming to the material assignments. So sometimes, like some popular materials are available in the library, right? Let us suppose that if material is not available in the library, what we have to do? We have to define the material. So how to define the material? You have to know what is the relative permittivity of material and what is the loss tangent. That is called as a tan delta sigma by omega epsilon. That value is given. Otherwise, you can calculate these values, right? Once you have calculated this value, if material is available in the library, easily you can select the material, right? Like copper, or maybe alumina material, or maybe Teflon material, or maybe Roger, or FR4. Some popular materials are available, but supposed to be, if you are going to work on the like advanced antenna application, maybe some materials are not going to be available. Or let us suppose that you have designed a material, so that in that case, how you are going to define. So this one, first you can assign the material. So for material assignment, what we have to do, one is the relative permittivity, and another thing is the loss tangent. So once you have defined the material, then you have to design the antenna. So what you have to do, you have to construct a patch, a ground plane, and you have to design a substrate. So let us suppose that either you can put the dimensions, but generally we are going to, like if we are going to put the dimensions directly, we are not going to put, we are going to put the variables. So let us suppose that why we are going to put the variables, because sometimes results are not, if you are going to design any antenna or filter, your result is not going to be appropriate, or it is not going to be suitable for a particular application. So you need the optimization. So for that one, again, you have to change the dimensions. So better you can put it from beginning onwards, like you have created any project. So by defining the dimension, you can put the variables like A, B, C, D, etc. Right. Once you have put it this one, they are going to ask. Let us suppose that in this case we have put it the length and width. So the dimension is going to be defined minus L by 2 to plus L by 2. So if you are going to click on the OK, they are going to ask what is the dimension of L, what is the dimension of TS. Once you have put it the dimension, your substrate is going to be created. Then ground plane is there. So actually in the HFSS, what is the here I am going to explain in the what is the difference between the HFSS, why CST is going to be more user friendly. In the CST, we have the two coordinates. One is called as a global coordinate, that is XYZ, right? And another one is the local coordinates are there, right? In HFSS, let us suppose that you have to define. Let us suppose that we have selected the subset from 0 to height is, let's suppose that 1.6 for the case of FR4. But again we have to create a ground plane, so what we have to think about, what we have put at the dimension. But in CST, no need to remember any dimension. Initially what you have put it for the ground plane, what is the height for the substrate, what is the height for the, so you just we have one local coordinate that is called as a WCF. You just select the face, and after selecting the face, you can align the uh, local local coordinate, that is called as a WCS. Once you have aligned the local coordinate, automatically it is going to become on the surface. So you can create the ground plane, you can create the radiating paths. Once you have created this one, so then you have to here two things are there. We have taken a coaxial fade. So for coaxial fade, you have to make you have to put the three cylinder. One is one have three cylinder. First cylinder have a outer radius of 2.5 to 2.25, and the material is the PEC. Next inner cylinder is the that is that is a Teflon material having a dimension of 0.63 to 2.25 to 0.63, and last cylinder is your PEC, and pin is going to be inside to your patch. So another technique is the microstrip feed line technique. So you can put the feed line. So for feed line calculation, we have the online calculators are there. You just put your like what is the width of your radiating patch, all the calculation and permittivity you can put in the online calculator. And for impedance, how much we have to put for 50 ohm, because you all know that in the microwave there is a trade-off between the low losses and maximum power. So this one we have taken the 50 ohm. So for 50 ohm we are going to do all the calculations. So either you are going to design a microstrip feed line or CPW feed line or coaxial line. So you have to think about this. We are going to calculate for a characteristic impedance of a 50 ohm. So once you have created this one, then coming to the you have to define the frequency range. So for which frequency we have to design. So let us suppose that I am going to put 0 to 6. Depending upon the application, you can put the frequency range. Once you have selected the frequency range, so here you can see that no need to select the mesh. Right now in the new this one we have taken from the old CST studio suite. In the 24, automatically mesh calculation is going to be done in the software. So once this calculation is going to be done, you have to put the excitation. Let us suppose that excitation, that means you have to define the port. So for defining the port, you just see the yellow color line. Here we have defining the coaxial feeding, and we are going to define the port. So this is the antenna. So only one port is going to be needed. So first we are going to select the face, and we are going to define the port. Once you are going to define the port, this two types of ports are there. Waveguide port setup is there, and love port setups are there. So we are going to define the waveguide port in our cases. So once we have defined the port, then it is going to become to the boundary conditions. So in HFSS, generally we have to make a boundary. But here, no need to make the boundary in the new CST. Actually, new versions of the CST, directly it is going to be take the boundary, right? So depending upon the, why, because initially we have selected the for a particular application we have created the project. So here no need to define the boundary, automatically it is going to be take the boundary. Some special cases are there, later we'll discuss in the detail. So once you have defined the boundary, so for antenna, we have the near field parameter, that is S parameters are there, and we have the far field parameter like your gain, directivity, right? So also surface current distributions are there. So here you can, in the navigation tree, in the CST navigation tree, you just see here in the box we have the field monitor. So what we have to see, like radiation pattern, gain. So you have to select the far field. Let us suppose that you have to see whether which component is going to be like we have designed any radiated element, whether with which particular section is going to be contribute the current. So how we can see by using the surface current analysis. So in the monitor we have the E field, H field, surface current, like current density, far field. So basically for the antenna cases we have to concentrate on the H field and surface current, E field and far field analysis, right? So in the far field, here two things are there. One is the frequency, another one is the broadband. Let us suppose that initially we don't know whether, let us suppose that you have designed a multi-band antenna or maybe any planar antenna for a particular application. You don't know whether this antenna is going to be radiate at which frequency. So we at that time we are not going to put the frequency directly. So first we can select the broadband and we are going to give the samples like 100 samples or 1000 samples. Let us suppose that I am going to explain. Let's suppose that you have a working range of 1 to 10 gigahertz and I am going to select a 100 samples. So how it is going to be take? So that is 0, 0 0.1, 0 0.2, 0 0.3, like that it is going to be select, or 1, 1.1. So depending upon, you can select the samples. Once you have selected this one, whether you have to see, because initially we are going to give all the field monitors. So by the navigation tree, you can see first we can select the field monitor. In the field monitor, what we have to see, whether E field, H field, surface current or far field. So we can select one by one. So first I am going to select E field, then we can put the frequency. Similarly, you are going to select the surface current distribution. Either you can put the frequency or you can put the broadband, or also you can put the frequency with the steps. Like supposed to be you are unable to calculate the sample. So what you can do, you can put the steps like a start frequency is 1 gigahertz, stop frequency 5 gigahertz. What is the step size? 0.1 or 0.01, depending upon. Supposed to be if you are going to put samples are going to be more, so your solver calculation time is going to be more. So accuracy is more going to be correct, right? So once you have selected once you have done the field monitor, so now you have to see the result. So before that, you have to see here two types of the solvers are there. One is the hexahedral, another one is the tetrahedral TMs are there. So here one more thing is there. What level of accuracy you want, like minus 30 dB or minus 40 dB, minus 60 dB. So depending upon, you can select the accuracy level. Here also in the S parameter settings, you can normalize with the fixed impedance, like we are going to normalize with the 50 ohm. And also one more option is there, adapting machine. But initially I am not going to suggest to do the adapting machine, because initially we don't know whether we have designed any component or any RF component or antenna, either antenna or filter or coupler. We don't know the working time. So if you are going to select the adapting machine, actually in the adapting machine, generally by default it is going to be take the 6 passes. But you can, like supposed to be, if you want more accuracy, you can increase the number of passes. So your calculation time is going to be more. So initially, it's my suggestion, don't select the adapting machine. Once you are getting the results, after that you can select the adapting machine. Like if a design is any antenna, whether result is going to be changed or whether result is going to be more optimized by using the adapting machine, we can check the latter. Once you have designed any antenna, or once you have designed any filter or any component, so supposed to be your final design is going to be prepared, then you can do the adapting machine. So after that we have the, in the dashboard you can see that file home modeling. It is one by one is there. Once you first you have to create the file, then do the modeling, then do the simulation. In the simulation we have the transient solvers are there. So here also three solvers are there. One is the time domain solver or frequency domain solver. So here we are going to select a time domain solver. So once you have selected the time domain solver, what it will take some time to do the simulations. After that you can observe that in the window you can see S parameter results are there. Also you can see the in the 2D results section, because we have a, in the 1D results we have like S parameters, radiation efficiency, total efficiencies are there, VSWR, admittance matrix, impedance matrix are there. In the 2D, in the navigation tree you can see that result section we have 1D results, 2D results and far fields are there. So in the 1D results we have the S parameters, that is also very important for any microwave components or antenna filter. Then we have the how much power level is going to be accept your antenna. Then we have the radiation, like efficiencies are there. If you design any antenna, how much it is going to be efficient. Then VSWR also you can see that, and admittance impedance matrices are there. In the 2D result section we have the like A field, H field, or surface current distribution. So by observing the field distribution you can see that particular stub or particular radiating element is going to be radiated or not. You can observe clearly, right? So in the last section in the navigation tree you have the far field, right? In the far field you can observe here, if you design any antenna, let us suppose that if you selected the broadband or if you selected some states, so different far field are going to become. So you can different radiation patterns are going to become. Like in the window we have a 20 to 30 results are there, right? Like it is going to be, we have the result of 1, 1.1, 1.2, 1.3 like that. Here already we have designed, everything is going to be fixed. Initially we have taken a frequency of 9.4 gigahertz. So that's why we have selected a instead of broadband you have selected a far field of 9.4 gigahertz. So basically it is going to be show the absolute value. So in the radiation pattern, this is a 3D pattern. You can also observe the, you can also see the polar plot or the 2D patterns are there, and parallelly you can see the co-polarization level, cross polarization level for the circular polarized antenna, like the LSCP, RSCPs are there. And in the template based processing you have the gain, axial ratio calculations, directivity, all these things are there. So now I'm going to share this CST window. I hope that this window is visible to all. Is it visible? This window is visible to all?
Yes, sir. It is visible to me.
Yes, sir. Thank you, sir. In the CST, initially I have created a template for the waveguide. So automatically you can observe that in the window antenna waveguide is there. Right now I am going to create a template for planar antenna. So let me select first. Here you can see that whatever I have discussed in the PPT, same things are there. So either in which domain you are going to work. This is entire studio suite. It is not only for the RF people. Optical people are also working in there. Like for if you are EMI, EMC testings are there, also they are going to work on this CS2 studio. So basically our domain in microwave. So first we are going to select microwave and optical. So in the here you can see that we have the antenna In the antenna, if I'm going to click the next, we have a different type of antenna in the workflow, like waveguide, planar, wire, phase array, mobile. This is a new template. In the PPT, we have the old version. So right now they have created a separate template for millimeter wave. So once you are going to work on the 5G or millimeter, so you have the different template. This is the CST 2024. Here also they have embedded the Python codes are there, right? So that is the advantage of this CST. So you have the 5G and supposed to be, if you are going to work on the circuit, so just click on the next. So here you can see that we have the waveguide and cavity filter, planar filters are there, waveguide coupler, dividers are there, planar coupler, like most popular couplers are there, rat size couplers are there. So you can design depending upon. So be careful. Once you are going to, let us suppose that if your research area is going to be specified, whether you have to work on the planar antenna or whether you have to work on the waveguide, or you have to design any component, whether it is a waveguide or planar components are there. So for different uh, different designs, we have a different workflows are there. So first you have to create a template. Once you have created, let us suppose that radar applications are there. So in the radar applications, like you have to do the RCS analysis. So for that one, different workflows are there. So be careful. So once you have selected the template, in which domain you have to work, based on that you can select the workflow. So let us, here I am going to select the workflow of antenna. In the antenna, we have a waveguide, planar antennas are there. So mostly people are going to work on the planar antenna. So I am going to select here planar antenna. Then go to the next. In the next, they are in the project template. They are going to ask uh, which type of solvers they are going to use, right? So here in the time domain, that is for the wideband multiband antenna. Frequency domain, that is basically for the resonant antenna, and multi-layer structure, that is a different things. Later we'll discuss in the detail if time permits. So here I am going to select a time domain. In the time domain, let us suppose that if you are going to work on the if you are going to work on the uh, if you are going to work on the terahertz or 6G, what you have to do in the dimensions, we know that in the micrometer. So you can select the micrometer. But here we are going to keep only in the millimeter because our work is only up to gigahertz, right? So here in the frequency options are there. It is going to be start from the hertz. In the microwave, gigahertz is there. So let us suppose that someone is going to work on the terahertz, like supposed to be 1 terahertz to 4 terahertz. You can also put the terahertz. Otherwise, you can keep as it is, and later you can put like 90 to 140 gigahertz or 100 to 200 gigahertz. Once you have selected this dimension and frequency is very important. Then go to the next. In the next, they are going to ask the minimum and maximum frequency. So here you can put the frequency, otherwise keep as it is blank, right? Because initially you don't know whether you have to design the antenna which application. Let us suppose that sometimes our sweep range is 1 to 10 gigahertz, 1 to 5 gigahertz. So we can keep the blanks. Go to the next, then click the finish.
Excuse me, sir.
Yes.
Sorry to interrupt you.
Yes. Yes.
Sir, earlier you have shown that frequency selection, dimension selection window. In that
Yeah.
time was also one parameter, time and temperature.
Yeah.
So, do we need that parameter?
Nothing. No need to change the time parameters.
Okay. Even temperature also we need not to mention.
Need not to mention. Automatically it is going to become. So we don't need to change anything.
Yes.
I think, sir, here temperature we are not changing because temperature is mainly vary the material quality. So whatever material you are selecting, that is depend upon the temperatures.
Yeah, that is different of for graphene based antenna. We have to vary with the temperature. That is the different discussions are there. So Kundan is right. So now I am going to come. So once we have created the template here in the project section, you can see that we have the two templates. One is the waveguide, another one is the planar antenna. So now I'm going to design the waveguide antenna. So after selecting the project template, after whom you can see that modelings are there. So in the modeling, we have a different different uh, components are there, like bricks are there, maybe torus are there, maybe cylinder are there, right? So depending upon what you are going to design, we can select. So initially we are going to design a waveguide, then slotted waveguide. I'm going to design different types of waveguide, and then we'll different type of waveguides, planar antenna, as well as coupler. So first, what I am going to do, let us suppose that for illustration purpose, I am going to select a WR90 rectangular waveguide. Every time we are going to use in the laboratory. So WR90 waveguides, its broad wall dimension is 22.86. That is called as A, and B is 10.16. Actually, the number 90, basically it is going to be denote the broad wall dimension, that is 0.90U, and if you convert in the millimeter, it becomes 22.86. So here first I am going to select a brick, right? So here I am going to design the waveguide by different techniques. So here I am going to select like minus, I am going to put the dimension minus a by 2 to minus t, a by 2 to plus t. T is the thickness of waveguide. Y dimension is minus b by 2 minus t. B is the narrow wall dimension of the waveguide. B by 2 to plus t. Actually, here I am going to create a sheet first. So what I am going to put? I am going to put the thickness 0. Two things are there. Either you can design a two waveguide and you can subtract one with another. That is a hollow metallic pipe is also waveguide. But here I am going to design a different. I am going to design the waveguide by using the sheet. So here material, either you can put the copper pure, alumina material, or PEC. So I am going to select a PEC. So if I am going to click here, initially we have put it the parameter. A is your broader wall dimension, that is called, and B is your narrow wall dimension. T is the thickness of waveguide. So I am going to design expand waveguide. So what is the dimension for the broad wall? That is 22.86. Then thickness, I am going to put 1.27 millimeter, and B dimension is, that is a narrow wall dimension, 10.16, right? So I have created one sheet. Again I am going to create one more sheet, right? So here I am going to put the dimension like A by 2 to plus A by 2 minus B by 2 to plus B by 2, 0, 0, right? So we have created the two sheets. What I am going to do now, I am going to do the Boolean operation. So I am going to subtract the I am going to subtract 1 with 2. So here you can see that Boolean operations are there: add, subtract, intersect, and insert. So I am going to subtract. We have to subtract solid 1 with solid 2. So just click on the, just put the enter. So it is going to be selected. What I am going to do here, I am going to extrude the face of the sheet. So first I am going to select the face of this sheet. So just click on the F. Otherwise we have the picks are there. In the picks, some shortcuts are also there. Like you have to select any edge. You just click on, just point the E. If you are going to select, just click on the F. Otherwise, here you can pick any one. Let us suppose that I am going to select the face. So pick the face. So just pick the face. So once face is going to be picked, now I am going to use the extrude options. So what we have to extrude, the face is going to be extruded. So let us suppose that we have to design a waveguide that have a dimension or length of the waveguide is 100 millimeter or 50 millimeter. So in the height, same things I am going to put. So I am going to put a 100 millimeter, right? I am not going to twist and taper. in the upcoming slide, same waveguide I am going to twist and taper. Uh, Planar structure, so many tutorials are available on the YouTube, but in the waveguide, if you are going to design, some conventional approach are there. So I'm not going to follow the conventional approach, because supposed to be, if you are going to design some annular waveguide, it is very difficult to bend or to twist the waveguide, right? So here I'm going to put the height. So you can observe here. Uh, so again, I'm going to do the Boolean operation. So just add both the solid 1 and solid 2. Fine. So you can see here the wave. This is the waveguide. Fine. So I'm going to measure the dimension, whether we have designed the waveguide, the dimensions are going to be correct or not. So just I'm going to put the edge, just pick the edge. So you can observe that here broader ball dimension is same 22.86. Now we have to delete the peaks. So what I'm going to do, I'm going to press D buttons. Otherwise here pick also delete options are there, right? So generally for age or for face, I'm going to use the shortcuts. For face, you just type the F, for age E, for point P, and for delete. Let us suppose that by mistakenly I'm going to select any face, and we have to remove this, or we have to deselect this. So what we can do, just press the D on your desktop, automatically it is going to be. So once you have designed the waveguide, actually you know that waveguide is going to be acts as a high pass filter. So every waveguide has some cutoff frequency. Let us suppose that this is a waveguide, expand waveguides are there. So formulas are there in any electromagnetic books. Formulas are given. You just use the formula to find out, to calculate the cutoff frequency of the waveguide. For this expand waveguide, we have the cutoff frequency of 6.58 gigahertz. But we are going to select the working range of waveguide is 8.2 to 12.4 gigahertz. What is the reason behind? Because at cutoff frequency, attenuation is going to be very high. So generally for every waveguide, either it is a X band waveguide or L band waveguide or C band waveguide, what range we have to select, because we have to satisfy the attenuation limit, that is 0.2 dB per kilometer. So we are going to select a range of 125 to 189% multiply with cutoff frequency. So if you are going to multiply your cutoff frequency with a 1.25, so what is the band of this waveguide? That is 8 point, lower frequency is 8.2 gigahertz, and if you are going to multiply with 1.89, it is going to be 12.4 gigahertz. Like that we have to select. So you can select the like once this modeling is going to be done, what we have to do, we have to come in the simulation. So in the waveguide, you can observe that two ports are there, right? Because this is a hollow metallic waveguide. Basically, it is acts as a high pass filter. So now to define the port, first you have to select this phase, right? Once you have selected this phase, here in the simulation, you have the frequency, background, bond rate, then waveguide port is there. Just click on the waveguide port. So automatically entire section is going to be selected. Otherwise, if it is not going to be selected in the planar, we have to do the some calculations like 5h plus mf. H is the thickness of your substrate, and depending upon the what is the width of the feed line, some calculators are there. If you are going to search on the YouTube, available are there, right? Contents are available for planar antenna. You can easily design the fit. So once you have click on the port, this port 1 is going to be defined. You just rotate your waveguide, fine, to define the port number 2. Similar steps you can repeat for the port number 2. Just select the phase, click on the waveguide port, and this port is going to be defined, right? Once you have defined the port, what you have to do, you have to define the frequency. We know that this is expand waveguide, so working range is working range is 8 to 12 gigahertz, but we have to see the cutoff frequency also. So what we can do, we can put like 6 to 12 gigahertz, right? So I'm going to put 6 to 12 gigahertz, right? So once you click, automatically boundary is going to be select. Now coming to the field monitor, we have to see the like E field at what frequency. Automatically frequency is going to become center frequency is going to become. But supposed to be someone is going to be check the field at different frequency. So for that one, what you have to do here, you can see that just click on the frequency list. Here stay with the linear, like supposed to be if you are going to select the frequency, so they are going to ask what step size you have to put, like 0 0.1, 0.5 or 0.6 or 1. So here I am going to put 1, right? If I am going to apply in the navigation window, you can observe here in the field monitors, like we have given the field. So A field is going to become at 6 gigahertz, 7 gigahertz, 8 gigahertz, 9 gigahertz, 10 gigahertz, 11 gigahertz, 12 gigahertz, right? So once you have done these things, after that you have to start the simulations. Fine. So I'm not going to start the simulations because we have to design the different waveguide. So what I'm going to do here, I'm going to design a slotted waveguide. So right now in the radar and satellites, we have the slotted waveguide, that is the antenna. So how we can create the slot in the top in the waveguide? Basically we have a 4 wall. One is the top wall, one is the bottom, and 2 side walls is there. So on the top wall you have to create a slot. So if we are going to design this, especially in the 3D structure in the HFSS, it will take time, because in the HFSS we don't have the local coordinates, but here also we have the local coordinate, where we have to create the slots on the top wall of the waveguide. Basically we have to create the slot, right? So what we can do, first I am going to select the top wall of the waveguide. So here I am going to select the top. Just click on the face, type F, or from here also you can pick F, right? So once you have selected the face, here we have a local coordinate that is called as a WCS, right? So in the local coordinate, I'm going here, we have a 2 options are there. One is the you have to align with WCS. So if you are going to align with the WCS, automatically it is going to become on the center. What is the, we have selected a waveguide that is a length of 100 mm. So at 50 mm, your coordinate is going to become, right? But at the center, we are not going to design the slot, because due to the phase cancellations, your slot is not going to be radiate. Let us suppose that we have to design a slot that we are not going to design on the center. Let us suppose that with the center, if I am going to say in terms of the dimension of U and V, we have to design a a slot that is far from in terms of U 4 millimeter, and in terms of V 10 millimeters are there. So what we have to do, we have to move our local coordinate also, right? So just move the local coordinates. So they are going to ask how much differential length you are going to move. So let us suppose that in the U I am going to move like 3 millimeter, and in the V you can put the positive negative values also there. So I am going to move like let us suppose that 5. You just see the preview. Before applying, you just check whether you have given the dimensions, whether it is proper or not. If it is not going to be proper, you just check your dimensions, right? Once you are satisfied with the dimensions, you just see the preview. Once you are going to satisfy with the preview, just click on the OK, right? Now here we have to design a slot. So what we are going to do, again in the modeling, I am going to design a slot, right? So slot having a length of 60 millimeter, that is going to be designed. This calculation already I have done for a frequency of 9.3 gigahertz. That is for the radar applications. So they are going to ask the dimension. What is the dimension of U? So whether you can put the value like minus M to plus M, or or you can put some parameters, right? And we, let us suppose that I'm going to put minus L2 plus L, and thickness also I'm going to put what is the thickness of waveguide? 1.27. So, but we have to put the value in the minus, right? So minus 1.27, fine. Minus 1.2720. Just click on OK. M, I'm going to put like 0.5. So the total dimension is 1 millimeter. L, I'm going to put 8. So minus 8 to plus 8, it is going to be 16. So now you have to same, you have to repeat the Boolean operation, because you have to subtract the solid 2 with solid 1. So what we are going to do this. So here you can observe that this slot is going to be created in the waveguide. Let us suppose that you have to make the different slots. So every time I'm not going to make the slots, right? What we can do, here we have designed a slot. So now what we can do, so just I'm going to do the translate options. Here in the navigation tree, you just right click on the solid 2. Here options are going to become, right? So in the options here, you just observe that here transform is there. Just click on the transform. What we have to do, let us suppose that multiple slots we have to create in the waveguide. So every time I am not going to put the slots, right? So let us suppose that by with a distance we have to create 5 to 10 slots in the waveguide. So what we can do, we can just make a copy how much slot we have to create. So you just see after 10 mm one more slot is going to be designed. So I'm going to put a repetition factor of 1. Let us suppose that you have to design 5 slots. So you can do the repetition factor of 5. So repetition factor, that means how many slots you are going to design, how many components. Let us suppose that in SIW structure, let us suppose that you have to create a via. So once you have created the via, then a particular radius or particular distance, the via is going to be inserted in the substrate. So once you have created one, then again no need to design all this one. You just use the transform option and do the repetition factor. Let us suppose that 20 vias we have to design. So 20 repetition factor you have to put, right? So what we have to design the slot in which dimension, like U, V or W. In W, so here I'm going to put like 12. Just see the preview, right? No, it is 16 is there. So here we have to put like 20, right? Just check the preview. So we have created one slot. Just apply here, right? Let us suppose that you have to create one more slot. In U dimension, how much we have to move? Let us suppose that I have to move -4, and in V dimension, let us suppose that you have to move -20, right? One more slot we have to design -20 or 24. Randomly we are going to do. So see here, one more slot is going to be created, right? Or so once you have designed this one, what we have to do, here I have created the 3 slots in the waveguide. So basically you have to subtract all the slots one by one. So do the Boolean operations, click on the solid one. Here we have the Boolean operation is the subtraction. Subtract how many? 3. All the slots we have to subtract for in the waveguide. Just click on the enter. So here you can observe that we have designed, I have designed all the slots inside the waveguide. Same this initially you have this the waveguide. This is your slotted antenna. So power is going to be radiated through the slots. So for antenna in the film, same in the simulations we have a 2 port. Otherwise 1 port you are going to just sort it. So once you have defined the port, here antenna we need the far field parameters. So here E field, H field, far fields are there. I'm going to just click on the far field. So automatically it is going to become on the center frequency. So we have selected 6 to 12 gigahertz. So what is the center frequency? That is a 9 gigahertz. But we have to see our radiation pattern at different frequencies. So what we are going to give the steps with the linear. So they are going to ask how much steps. So we are going to put like 1. So it is we can see in the navigation tree, uh, field monitor is going to become at 6 gigahertz, 7 gigahertz, 8 gigahertz, 9 gigahertz, 10 gigahertz, 11 gigahertz, 12 gigahertz. Once you have done these things, let us suppose that in the antenna we got the S parameter, we got the surface current distribution, we got the H field, we got the radiation pattern. Then one more important parameter is there, that is the gain, directivity, front to back radiation ratio. So for that one, what we have to do, in the window, you just see after modeling simulation is there. In the simulation, post processing is there. In the post processing, we have a template based processing, that is called as a result template. You just click on the result template. In the result template, they are going to ask select the template group. So you just select, we need the far field results. So I'm going to select far field and antenna parameters. Then they are going to ask add the properties. So what we have to see, we have to see the far field result. So just click on the far field result. So in the separate window, different parameters are going to become like directivity, front to back radiation ratio, gain or maximum gain over selected frequency. So I'm going to select maximum gain over frequency. So we just check the setting whether it is correct or not. So automatically it is going to become on the broadband. If it is not going to become on the broadband, you just select on the broadband, right? This is the 3D. So just click on the OK. So why we have selected this template based processing? Because once you have simulated your antenna, then again you have to repeat the same process. So by the first simulation, in the first iteration, if you are going to put all these things, you can calculate all the parameters in the first result also. Otherwise, again you have to repeat the same process. Same for the antenna. This is a directive antenna. So we have to see the let us suppose that front to back radiation ratio. So just click on the front to back radiation ratio. Let us suppose that some antenna is a circular antenna. This is a linear polarized antenna. So for circularly polarized antenna, you have to see the axial ratio, right? So for axial ratio, you just select the directivity. Here you have to do some settings, right? Here you just select the broadband. In the broadband, what is the operating frequency, operating band? That is for this particular case, I have selected 6 to 12 gigahertz. So that is fine. Then actually the axial ratio plot is the Cartesian plot. So in the output data type, by default it is going to become polar plot. So we have to change in the Cartesian. I'm going to select 1D Cartesian. And if you are going to measure axial ratio, or if you are going to calculate the axial ratio, what we have to do, we have to see in the broadband, in the broadside direction. So what we have to do, we have to put phi 0 and theta 0. So I am going to put phi 0 and theta 0 also, right? So after this, in the right hand side, we have the far field setting. Also you have to see here the plot mode. You just select the gain, and here in the axis polarization, here absolute value is going to become. So you just change the absolute value, that is called as a, after the absolute you just change the axial ratio, because for circular polarization we have to check the axial ratio. Ideally it is a 0 dB, but for the practical application, if your graph is going to be fall below the 3 dB, you can say that your antenna is going to be circularly polarized, provided your return loss bandwidth and the axial ratio bandwidth is going to be same, or it is going to be overlap, right? If it is not going to be overlap, we are not going to show that your antenna is going to be circular polarized. You just click on the OK. So after the setting the result template, you can start the simulation. In the simulation, we have the transient solvers. So they are going to ask hexahedral, you can start. So here you can observe that meshes are going to be created depending upon which type of structures are there. Here meshes are going to become. So once you have designed your antenna, then do the post processing. After the post processing, you can start the simulation. Otherwise, you can do the simulations. After the simulations, if you have given the far field, broadband far field, also you can calculate the gain, directivity, axial ratio later. Once you are going to satisfy your result with the S parameters, so later you can also calculate the gain and other far field parameters. So this is one of the slotted waveguide. Let us suppose that someone is going to be design a twisted waveguide. How we are going to, let us suppose that you have to design a horn antenna. So or maybe any type of asymmetric structure or any annular waveguide is there. So especially UG PG students are going to be find how to design this type of 3D structure. So I'm going to illustrate these things within a couple of minutes. Same process we have to repeat, do the modeling. So here I'm going to create the sheet. So same steps are there. So directly I'm going to design. So minus a by 2 to same. I'm going to put all these values. So they are going to ask what is the dimension of A, what is the dimension of what is the thickness of waveguide, what is the dimension of the narrow wall. So once you have put it all this dimension, then create the second sheet, right? So that is minus a by 2 to plus a by 2 minus b by 2 to plus b by 2. Here thickness also I am going to put the 0. So why I am going to take the sheet? I'm going to explain. Now here we have to extrude our waveguide. Now what we have to do, we have a design a twisted waveguide. Let us suppose that the twisted waveguide have a length of 160 mm, right? So I'm going to put any route.
Uh, Sorry to interrupt you, sir. Actually, time is approaching.
Oh, just within 5 minutes I'm going to conclude.
Okay.
Fine. So I'm going to put here the height. Height is 160, and how much twist we have to, like you have to twist your waveguide 360 degree, right? So you just see here how we have designed this twisted waveguide, right? Let us suppose that you have to taper your waveguide. So same procedure is there, right? So just select the face, and for horn antenna tapering is there. So let us suppose that I'm going to put a height of 100 mm. Let us suppose that how much tapering angle is there. If you know the tapering angle, then it is fine. If you want to change the tapering angle, also you can change. You can push the you can put the twist also. Let us suppose that you can see that how it is going to be twist and tapered, right? And also with the slot, let us suppose that twisted horn is there, right? So twisted horn right now if you find the literature, very few contents are going to be up. So like that you can design a different types of waveguides, right? For planar antenna, we don't have the time. Actually, this discussion, if we are going to design any magic tee or any gap type of waveguides, so it is going to be take the time. So we have designed different types of antenna. Just I am going to show. I think it is not available in the my my desktop. Fine. Just I'm going to show the results, right? Because Kundan is told to me we don't have the time. I have to conclude the session. So this is a expand waveguide. So we have designed a slotted antenna. So basically, you can observe that here the cutoff frequency of the waveguide, it is almost 6.58 gigahertz is there, right? Almost it is 6.5 is there. Then your antenna is going to be radiate at 7.74. Fine. And also you can see the 2D results, right? How field is going to be. We are going to animate the field, right? So generally, actually waveguide is going to be support the dominant mode. So T10 mode is going to be T10 mode is going to be propagate at the port of the waveguide, right? So and mostly the waveguide current is going to be propagate through the walls of the waveguide, right? So we can also observe here the far fields are there. So in the far field, you just see supposed to be if I'm going to select a 9 gigahertz, so radiation pattern is going to become. So here also you can see the structure. Here you can observe that how slot is going to be radiate. So in the 3D pattern, actually we have designed the slot on the broad wall of the waveguide. So basically it is going to be radiate in the radiate through the slots, but we have to see the copole or cross pole. So for that one, I'm going to see the polar plot. So in the polar plot, we have the absolute. You can see the both the things like the co-poles and cross poles also. Right. Once you have checked these results, already I have given the result template. So you can check the gain. What is the gain? What is the directivity? So basically, the gain is almost 8.78 gigahertz is there. So right. So at 9 gigahertz, our gain of the antenna is 8.9 gigahertz. This is a directive antenna. So maybe the front to back radiation ratio is also there. Around 20 dB is there. And this antenna is a linear polarized. So you can observe that in the graph, we are not getting the axial ratio bandwidth. 3 dB axial ratio bandwidth are not there. So basically, this antenna is a linear polarized. Supposed to be your antenna is going to be circularly polarized. So in that case, the axial ratio bandwidth is going to become. So based on that, you can check the results. Right. So on this note, today I am going to stop my discussion at this point. So we have a very short time. So I have not designed all the antenna. So if you have any doubts, you can tell me.
Okay, so now house is open for the questions. So dear participants, you have any query regarding to the guide, then you can ask with the sir.
Hi sir, this is Manu sir. Hello.
Yes, sir. Yes, sir. Yes. Tell me, sir.
So previously that whatever A2 code you have shown that can you tell me that what is the frequency range like working range that waveguide?
For waveguide, actually in the waveguide, for every band we have a fixed waveguide. Like same dimension we are not going to do. In the planar antenna, actually we are going to do the heat and trimeter. Sometimes some calculations are there. But in the waveguide, if you see the data sheets for each and every waveguide, dimensions are going to be fixed. Like WR187 waveguide, that is for the C band waveguide. So dimensions, what is the number of waveguides? Suppose that WR90, what is the name? Waveguide rectangular, and 90 basically 0.90 inch its broad wall dimension. Similarly, if you are going to work on the terahertz antenna, let us suppose that we have a WR8 waveguide, WR2 waveguide. So what is the broad wall dimension? 0.08 inch, right? So almost 2 millimeter broader wall dimension and 1 millimeter narrow wall dimension. In the dimension of waveguide, we are not going to be changed. Even in the slotted waveguide, everything for the design of the slotted waveguide, mathematics are there. Based on the mathematics, you have to design the slot, you have to fix the offsets. That is the theoretical discussion, right?
Yes, sir. And sir, like, what is the basic difference between that your waveguide structure and leaky wave antenna?
So leaky waveguide antenna is a different thing. That is a like for which applications you are going to ask for leaky wave antenna?
Sir, for beamforming, by changing the frequency here also, if you change the frequency, the beamforming tilting is like, by changing the frequency, beamforming is also changing, I think. Even in leaky wave antenna also, I have shown that, like, I have seen that by changing the frequency, beamforming, like beam tilting is happening by cutting some slot on the waveguide.
So, sir, leaky waveguide antenna is a different thing, right? So,
Yes,
you
sir.
are asking in terms of the theoretical, what is the difference, right? So, in the leaky, I think in the leaky waveguide antenna, like we need the narrow beams are there. So, same waveguide we can use there. Nothing is there. Like gap waveguide, technologies are going to be different. Right now, I have not worked with the leaky waveguide, so I don't have idea. Maybe Kundan have more idea about the leaky waveguide.
Okay, thank you.
We work for the gap waveguide technology. I think for gap waveguide technology, similar things we are going to use. Fine. Any more doubts?
So can you explain a little bit about the boundaries and background settings? Why it is
Bond
necessary?
No, no. Actually, background setting is necessary. Actually, in the HFSS, like boundary, we have to define whether perfect electric conductor, or we have to define all the things in the. But in the CST, in the back end, they have already defined the boundary. So that's why initially we have select the project template, right? So we are not going to give the boundary. We are not going to put the boundary condition, especially some conditions like you have to do the metamaterial analysis. That in that case you have to see which type of boundary is going to be needed. Based on that you can define the boundary. Otherwise, like antenna, filter, everything they have predefined. That's why initially we have to create the template for like waveguide. Different templates are there, and for planar antenna, different templates are there. But if you are going to work on the HFSS, you have to define the boundary like radiation boundary, or you can see that perfect electric conductor boundary. That thing you have to define. But CST automatically it is going to become. So we are not going to define the boundary. So that's why the background setting is going to be important.
Background settings are to be defined in planar antennas and waveguides, not in metal surfaces like yes. Sir.
For everything it is going to be defined. Even meta surface also template is there, right? Meta surface, that is periodic structure is there. Na? In the periodic structure, I'm going, just a minute, I'm going to open the CST. I think my screen is visible. Yes,
Yes,
or
sir,
no?
it is visible.
Okay. So in the new, you just click on the create. Let us suppose that they are going to ask where you are going to work. Like periodic structure are there. In the periodic structure, FSS metamaterials are there. Frequency selective surface metamaterial, like you are. So that's why no need to define the boundary. Don't worry about the boundary. Let us suppose that you have selected a different template. In that case, you have to do the background settings. But in CST, in the recent version like 23, 24, they have upgraded all the things for metamaterial, FSS structure, metamaterial full structure. Already you have, initially you have to do the settings. Once you have done the settings, then no need to do the boundary settings, all the things. That is the advantage in the CST, right? Also in the CST window, just I am going to say, you can see that here also Python settings are there. Right now uh, some antenna, some coding techniques are going to be needed. So you can embed your code in the Python, right? Once you have wrote it, so you can embed your code with the Python, and you just see the your result whether it is going to be validated or not. So they have in the CST 24, 23. If I'm going to say that after 2022, so many uh, new so many new sections are going to be embedded in this software, right? Fine. So no need to worry about any boundary conditions. If you are going to work on the HFSS, like then you have to worry about the boundary condition. In CST already boundary is going to be defined. If you want to check, you can check the boundary also. Like whether this boundary, because they have the predefined boundary. Based on that, what technology is going to be available. Let us suppose that you are going to work in the new technology. For new technology, if you are going to set the boundaries parameters, then you can set the boundaries here, which type of boundary you are going to need it, right? So whether it is a radius, here you just observe that what type of boundaries are there. You can apply all the direction. Otherwise, you can change the boundary. Whether the electric boundary you are going to change, magnetic boundary or open boundary or conducting wall, or in your case you are going to say that unit cell. You can change the boundary also, right?
Yes, sir. Thank you, sir. Sir, what about the mesh settings? That why it is so necessary to tickles with the mesh settings?
Mesh settings is not required in the CST right now. Right now, it is not going to be required.
Okay, sir. Thank you, sir.
Yes, sir.
So any more questions from participants side?
Hello, sir.
Yes, sir.
Sir, a very nice presentation by you, sir. Thanks to you a lot.
Welcome, sir.
I have one question, sir. At the end, you have shown bending of a waveguide.
Yes, yes.
Does it affect the radiation?
Uh, Bending also, definitely it is going to be, actually bending and twisting, basically it is going to be used for the, actually it is going to be used for the slow wave structure. So definitely it is going to be affect the radiation. If you are going to design a twisted waveguide, so it is going to be so the like slotted waveguide is there or bending structure are there. So maybe it is going to be so the circular polarization in some directions, like in fire direction also, maybe in the broadside direction. So we can say that definitely it is going to be affect the radiations.
Okay, sir. Thank you.
Even it is going to be affect your cross polarization level also there, because if you are going to twist or bend, your waveguide structure is going to be slow. So you will achieve the high gain, but parallelly you have to compromise with the cross polarization level.
Okay, okay. Fine, sir.
Any more question?
Hello, sir.
Yeah. Good afternoon.
Am I audible?
Yeah, you are audible.
Good afternoon. Sir, actually, I'm stuck in my design. Can we do heat analysis in CST?
Heat analysis. Yeah, you can do the heat analysis. Supposed to be right now here. If I'm going to explain, it will take that time. Kundan have my number and email ID. Separately, you can discuss with me. Right.
Oh, okay, sir. Thank you so much.
Okay. Any more question?
If any questions are there, if you are facing any issues, Professor Kundan have my email ID and my number are also there. He can share the details. He can share my details also, right?
Okay. So those participants who are interested to take the number of the Dr. Avinash Chandra sir, you just give me the message in our WhatsApp group. I will provide you. Okay. So thank you very much, sir. So you have joined us in a very short notice, and your expertise is very fruitful for the audience, even for me, because you have completely give the demonstrations on CST, how to design the waveguides, how to twist the waveguides, how to design the waveguide slot array antennas.
Thank you, sir.
And it is really fruitful for all the participants. So thank you very much, sir.
Thank you very much. Thank you to all for
Okay, thank you,
listening.
sir.
Thank
So
you.
I
Bye
think
bye.
you can leave from here, sir.
Yeah, thank you, sir.
Okay. So now, dear participant, the same link will you work for tomorrow, because we have developed a single Google Meet link for all the sessions. So you can join the through same link in tomorrow's session, which is 8 a.m. Sorry, 10 a.m. You can join before 5 minutes of starting the session. So thank you very much, sir. And I have already shared you the attendance come feedback performer to you. You just fill out the Google form, and your attendance is marks. And we have also marked your attendance here, which is available in the online mode. Okay, so thank you everyone. So we will meet tomorrow at 9:55 a.m. So thank you everyone.